Hello guys, I am Munot and welcome to the School of Physics. Please subscribe to my channel and today we are going to do properties of matter. Properties of matter, yeah, you heard it right, properties of matter within a few minutes. Direct questions on formulas in the exams, let's do it. Okay, so properties, today we are going to do properties of matter. Okay. Properties of matter. So properties of matter में what are we going to study? We are going to study about stress, strain, then bulk modulus, Poisson ratio, a lot of such things. So let's begin. Okay. So stress is equal to force upon area. So suppose I have, okay, I'll make a bigger figure. Suppose I have something like this, okay, and I am applying a force F on it, and this area is A. Suppose because of this force might be in any direction, say this direction, right? So because of this force, if there is some kind of an elongation in this direction, its initial length is L, and there is some elongation delta L in the longitudinal. This direction is called longitudinal direction. So there is some elongation in longitudinal direction, some elongation in latitudinal direction because of this force. This latitudinal or say lateral initial length is x, and now it has grown to delta x. Okay, x plus delta x. So there is some deformation here, and this angle is say phi. Okay, so what is the stress? Stress is equal to force upon area, that is force in the x direction upon the area. Okay, what is the strain? Strain is equal to, strain can be of three types. One is longitudinal strain. It is given by delta L upon L. Okay, lateral strain is given by delta x upon x. Then there is another strain called shear strain. What it is called? Shear strain, and it is given by tan phi is equal to delta x upon L. That is, shear strain is tan of this angle phi. Okay, so this is about stress, this is about strain. What is the Poisson ratio? What is the Poisson ratio? So Poisson ratio is equal to lateral strain. Poisson ratio, okay, Poisson ratio, we denote it like this, is equal to lateral strain number 2 upon longitudinal strain, that is 2 upon 1. Lateral strain upon longitudinal strain. Then what is the Young's modulus? Young's modulus is equal to stress upon longitudinal strain. Stress upon longitudinal strain. What is the stress? It is force upon area. So this is Young's modulus. Then what is the bulk modulus? So we write bulk modulus as so bulk modulus formula is very easy. It is written as minus of V dP by dV, minus of volume change in pressure upon instantaneous change in pressure upon instantaneous change in volume upon volume at that time. Now there is another thing called compressibility. Compressibility is the inverse of bulk modulus. So compressibility K, it is called compressibility. It is the inverse of bulk modulus. So these are the basic formulas. You can have a look over them from the beginning. So these are the basic formulas of properties of matter. Now the next thing that we are going to talk about is the viscosity. Okay, viscosity. I hope this is clear. Okay, so we'll go for viscosity. Okay, These are the basic formulas for solid. Okay, so viscosity, in viscosity what happens is, I'll give you a very simple case. So we write here viscosity. Okay, so in viscosity what happens is, suppose I have a ball here. The radius of this ball is equal to radius r, and the viscosity or dynamic viscosity of this fluid is, say, n. Okay, now what I'll be asked is, now suppose the velocity of this ball falling down. So there's this force mg going here, then there's this force F of buoyancy that we have studied, force of buoyancy we have studied, and there's another force of say F of drag. Now whenever the liquid is viscous, till now we have in fluid mechanics we have dealt with liquids which are not viscous, so which is water. Now here the liquid is viscous, so there will be a viscous force or drag force acting upwards. Okay, so at any point the velocity of this ball falling is v. So you will be asked, what is this force drag? So for this force drag we have to write 6 pi. R is the radius of the ball, r into n into v. N is the viscosity and v is the velocity of this ball falling down. Now there will come a point where force mg, that is the downward force on the ball, will become equal to force of buoyancy plus force of drag. At one point force of buoyancy plus force of drag will become equal to mg, and after this point the velocity will be constant and it will be the maximum achievable velocity, and it will be called as terminal velocity, right? So when it will be asked what is the terminal velocity, we'll also need the densities. So suppose the density of the ball is rho s and the density of the liquid is rho l. So to find terminal velocity we can have a very simple formula: 2 by 9 r square into g. G is the acceleration due to gravity. R square by g into rho s minus rho l, that is density of solid ball minus density of the liquid, upon the dynamic viscosity of the liquid. So this is the formula of terminal velocity. Both are very direct questions asked directly: 6 pi r into n into v, and this is the force of drag, and this is the terminal velocity, which is equals to 2 by 9 r square g rho s minus rho l upon n. Now the basic definition of viscosity. Viscosity depends on the gradient of velocity. So viscous force at any moment, you won't be needing this formula directly a lot of times, but viscous force is equal to force upon area. The area is the area on which this viscous force is acting, is negatively proportional to the gradient of the velocity in x direction, or in the direction in which force is acting. So viscous force upon area is directly proportional to the negative of the gradient of the velocity, and to remove the proportionality we add a constant, and this constant is called viscosity. Okay, next, talking about surface tension. So we'll talk about surface tension. So what is surface tension? Surface tension, listen very carefully. What is surface tension? Hold on. So here we write surface tension. Okay, now we have to write surface tension. So surface tension is the amount of work. So suppose there's this a balloon, okay, and I pull this balloon and increase its area. So the amount of work that will be required to increase its area by 1 unit is called the surface tension. So surface tension, suppose I have this balloon, okay, suppose I have this balloon and this is some line, and I pull it with force F, and this is the line L. So one way of defining surface tension, we can write it S or T or T. So it is the force acting on a particular line to something that is stretched, or we can write the work that is required to increase the area by 1 unit. Work or the energy that is required to increase the area by 1 unit. Okay, so this is surface tension. The surface tension, suppose this I'll discuss 3 things. One is a soap bubble. Okay, so in case of soap bubble, whenever there's some surface tension T, right? Whenever there is some surface tension T, what happens is it develops some kind of an excess pressure inside the soap bubble. So what is that excess pressure? That excess pressure is given by the formula 4 times of radius of this soap bubble are 4 times of surface tension upon radius of this soap bubble. Okay, then suppose there's this air bubble inside some liquid, okay, air bubble, or say a drop, a water drop. Okay, so for them the axis pressure that is developed is given by 2 times of surface tension upon radius of the air bubble or the drop. Okay, direct questions will come, you just have to remember which is given, soap bubble or air bubble or water drop. Okay, then there is another thing which is called capillary rise. Okay, capillary rise. So capillary rise has a very simple formula. Capillary rise, it is 2t cos theta capillary rise. Okay, so what happens in a capillary rise is I have this beaker, okay, and I have a capillary like this, and this beaker has water. So when I insert the capillary, what happens is the water, it kind of rises to a height h. We call this rise h height is capillary. Suppose the radius of this capillary rise, suppose the radius of this capillary is r, and this angle with the vertical is theta, and there's this viscosity. So there's this viscosity of the liquid called N, and suppose the surface tension that is acting is T. So the formula for the capillary rise is H formula is 2t cos theta, you can see 2t cos theta upon rho into r into g. Sorry, we don't need viscosity here, we will just need the density rho of the liquid. So capillary rise is 2t cos theta upon rho rg. So friends, this was our short lecture on completing all the properties of matter. You just have to revise these formulas again and again, and I'm sure you'll be able to do any kind of questions that will come from in the exam on this topic. And thank you for watching this video. Please subscribe to my channel. Thank you once again. Please subscribe. Thank you.